Hello everyone. In this video, we will be continuing module 3 introduction where we will be discussing about shaft design, and related to that we will be discussing few more formulas that will come under ASME details. So first of all, we should be knowing the general informations about the power, torque and speed, which is directly connected with the shaft design. So for the linear motion, we know that power is equal to force into velocity, and for the rotational movement, power is equal to torque into angular velocity. So this torque can be written as T, and angular velocity is written as omega. And we know what is the unit of the torque. It is inches in length they have given. Even if you want means you can put it even in Newton mm also we can put. And for the angular velocity is radians per second I have given. And if you are not comfortable with radians per second, you can go with any other unit, that is inches or like whatever the values you are comfortable, you can go with this. And what is the formula to find out this angular velocity is nothing but 2 pi n divided by 60. For the problem what we discussed, where if you know the power value and the speed value, means it is possible for us to find out what is the angular velocity and the total power value also we can able to find out. And so from this I'll be finding out, since I know the power value, so I'll be finding out the torque value as 63,225 h horsepower, and the torque value totally where in case if I'm looking for in Newton mm, the value will be 955,000 kilowatt per N. And here the shear and the bending stresses on the outer surface of a shaft for a torque and the bending moment m. So for the solid circular section, we know that the tau is equal to T by J into R, which is equal to T divided by pi d power 4 divided by 32 into D by 2. So after simplification, we will be getting it as 16T divided by pi d cube. Similarly, for the stress, sigma is equal to m by R, m by I equal into R. And again, I know what is this inertia formula for the solid circular section. It is m divided by pi d power 4 by 64 into d by 2, that is 32 m divided by pi d cube. For the hollow circular section, that is tau is equal to T by J into R, which is equal to T divided by pi d naught power 4 minus d I power 4 by 32 into d naught by 2, which is equal to 16T divided by pi d naught power 4 minus d I power 4 into d naught. And after simplification, I will be getting 16T divided by pi d cube into 1 minus lambda power 4, where lambda is nothing but di minus du. Similarly, for the stress, it is m by I into R, that is m divided by pi into do power 4 minus di power 4 by 64, that is do by 2, which is equal to 32 m divided by pi into do power 4 minus di power 4 into do, which is equal to 32 m divided by pi d cube into 1 minus lambda power 4, where lambda is equal to di by d naught. So here indirectly we can remember, always for the stress it is 32, and for the shear it is 60. And the principal normal stresses and the maximum distortion energy failure criterions for the non-rotating shafts, where the stress at a point on the shaft is a normal stress in x direction and the shear stress in xy plane. So we know that from the Mohr-Circle relation, S1 is equal to sigma by 2 plus square root of sigma by 2 square plus tau square, and S2 is equal to sigma by 2 minus square root of sigma by 2 whole square plus tau square. And the maximum distortion energy theory states that S1 square plus x2 square minus S1 S2 is less than or equal to SYP by n whole square. So putting values of S1 and S2 and simplifying, here you can able to see this, where the x-axis and y-axis relations is clearly mentioned here, and even the principal axis is shown in this 2D plane also. By using this, we can able to find out the design equation for the non-rotating shaft. And finally, we will be getting the equation as sigma square plus 3 tau square less than or equal to s divided by n whole square. This is the design equation for the non-rotating shaft. Then when we speak about the shaft design, we have three basic categories. That is for the axial loads, for the bending loads and the torsional loads. We need to remember the formula for both solid and the hollow shaft. First, let me discuss the formulas for the axial load. That is for the solid shaft, it is 4f divided by pi d square, and for the hollow shaft, it is 4f divided by pi du square minus di square, where du and di indicates the outer diameter and the inner diameter. For the bending loads, even for the tension and the compression, the same case. First, for the solid shaft, it is mbr by I, that is 32 mb divided by pi d cube, where I value have converted, that is the inertia value have substituted. And for the hollow shaft, it is 32 mb do divided by pi do power 4 minus di power 4. And for the torsional loads, for the hollow shaft, it is Tr by J, that is 16T divided by pi d cube, and for the hollow shaft, it is 16T do divided by pi do power 4 minus di power 4. And you can able to see here some of the common shaft loading mechanism, where we have the spur gears, we have helical gears, we have chain drives, we have spiral bevel gears, we have unbalanced mass, and we have belt drives. So all these things are some of the examples of the shaft designs. And here we have one more important concept, that is the ASME shaft equation. So this ASME is a basically a code equation for the hollow shaft, which combines torsion, bending and axial loads by applying the maximum shear equations modified by introducing shock, fatigue and column factor. And the equation we will be getting, that is d naught cube, which is equal to 16 divided by pi sigma s into 1 minus k power 4 square root of kb mb plus alpha FAD FADO into 1 plus k square by 8 the whole square plus kt mt whole square. For the solid shaft having the little or no axial loading, the equation is dO power cube, which is equal to 16 by pi sigma s into square root of kb mb whole square plus kt mt whole square. And these equations are available in the design data handbook. So directly we can adopt this equation from the design data handbook. While solving the problems, you can observe all the related equations, where the k is nothing but di by d naught, that is nothing but the radius of gyration, and d was the outside shaft diameter, and d is the inside shaft diameter, and the kb is nothing but the combined shock and fatigue factor applied to bending moment, and k is nothing but combined shock and fatigue factor applied to the torsional moment. So for the commercial shaftings and all, the allowable stresses, which is equal to 55 megapascal for the shaft without keyway and 40 megapascal for the shaft with keyway. And for the column action factor also, where the unity for a tensile load value is given, that is L by K should be always less than 1150, and for the alpha is equal to L by K, that should be 115 for the compressive load. And where this value is also given the factor of safety starting from 2.25 to the 1.6 value, where we can able to adopt. And this is the shaft equations, where it is continued here for the different loads. This is the table which I took it from the design data handbook for the stationary shafts. So where for the kb and kt, for the different the load gradually applied means for kb it is 1, and for kt is again 1. For the suddenly applied load, the kb value ranges from 1.5 to 2, and even for kt it is same. For the rotating shaft, the gradually applied loads, the kb is 1.5 and kt is 1, and for the minor shock suddenly applied load is 1.5 to 2, and for the kt it is 1 to 1.5, and where the heavy shock loads are for kb it is 2 to 3, and for kt it is 1.5 to 3. Then the design of the shaft for the torsional rigidity, it is based on the permissible angle of twist. That is the amount of twist permissible depends on the particular application and varies about 0.3 degree per meter for machine tool shafts to about 3.0 degree per meter for line shafting. And for the solid shaft, the theta is 584 mtl divided by gd power 4, and for the hollow shaft, theta is equal to 584 into mtl divided by g into d power 4, do power 4 minus di power 4, where the angle is nothing but theta is nothing but the angle of twist in degrees, L is nothing but the length of the shaft in meters, and G is nothing but torsional modulus of elasticity in Newton per meter square, where the length value always should be substituted per meter only. And these are the standard sizes of the shafts. These sizes vary according to the material specification and supplier. Typical sizes of the solid shafts are up to 25 mm in 0.5 mm increments, 25 to 50 mm in 1 mm increments, 50 to 100 mm in 2 mm increments, and 100 to 200 mm in 5 mm increments. And here you can able to see the bending and the torsional moment. Just now we discussed the formula for the belt drive and gear drive in the video one. So by using this formula only, we have solved the problem, and these are the main factors which influence the shaft design. So one of the first steps in the shaft design is to draw the bending moment diagram for the loader shaft, or the combined bending moment diagram if the loads acting in the shaft are on more than one axial plane. So from the bending moment diagram, the points of critical bending stress can be determined, and the torsional moment acting on the shaft can be determined from the formulas. And these are the some of the bending moment moment consideration and the stress concentration conditions for all those things. So with this, I'll be winding up this video. Thank you.